Great. Thanks for coming to my talk. My name is Adam. I'm going to be talking about vulnerability management in the supply chain space, supply chain security. The brief introduction. My name is Adam. I lead SemGrep supply chain, the engineering and product orgs. I started at R2C as a staff engineer, and I love building things and had the pleasure of building a bunch of open source security tools these last couple of years. I work at R2C. We build and maintain SemGrep, which is an open source static analysis tool. But before we get into the meat of the talk, I want to tell a story. Just going to journey us back to 2006, so long time ago. These three MIT grads co-founded a startup called Meraki, which is a cloud managed networking company. And they, being typical startup people, they chose a web framework. They chose Ruby on Rails as a tool to help them build their startup for the first time. They cared about networking, not so much about building perfect, performant, secure web apps. And over time, like most startups, they pivoted a bunch. They moved quickly. They played fast and loose with best practices, but they were small and not really a security target. And so they could just kind of get away with stuff. And we hear this story a lot, that when a company is in its early stage, they don't have to have perfection. Let's fast forward a few years to 2015. And Cisco acquires Meraki. And so like many startups, they have to go through some transformation. Also in 2015, this software engineer joined the cloud team, bright-eyed, ready to take on the world. My partner loves when I put up young at me on the screen. I look silly, but excited. At the time, there are 50 software engineers or so at the company. They have a few successful products. They're making quite a lot of money. But two things happen is because Meraki starts to become a bigger company, it starts to become a bigger target. And because we're acquired by Cisco, an even larger company, less risk is tolerated. And as the size of customers increases and the risk profile goes up, we decide to start a security team for the very first time. If you can imagine, we waited that long. And they're tasked with leveling up our security program. So one of the first things they saw is that we'd only upgraded Ruby on Rails one major version from 2006 to 2015. That's in 9 years, we'd gone up one major version. The most recent released major version of Rails at the time was version 4, and we were only a few months out from version 5's release, which meant the end of life for version 4 was, for version 3 was coming up soon. And the older version that we were on had a ton of vulnerabilities, and as we also looked at end of life, we weren't even going to be aware of the future vulnerabilities we were going to be running into. So you might be thinking the obvious thing to do here, let's upgrade. Sure. Just bump it one major version. And then the team can try to eventually move to new versions. So a few of our most senior engineers who had done that previous upgrade, they got in a room, they worked for a while, they did some architecture reviews, they tried to come up with a time estimate for how long it might take to upgrade this version from Rails 2 to Rails 3. One engineer said, I can do it in a weekend. And I'm sure we've all heard stuff like this before, very optimistic. But the realities of upgrades at larger companies and larger environments are that they're complex. At the end of the day, this group of people, they had no real idea how long this was going to take. They estimated maybe a small team could do it in a quarter, but they were just going to have to try. There was no other choice but to try, but they were going to have to try. But that turned out to be an optimistic estimate. It ended up taking over a year, a lot more than 3 engineers, and basically everybody in the cloud org worked on the upgrade in some way, shape, or form. That bright-eyed engineer, myself, who was really excited to come in and build features and solve problems, I spent most of my first year and a half with the team working on that upgrade. Either working on bug fixes, trying to find places where we didn't have the observability to figure out where things would break. And then since that first upgrade took so long, by the time we finished, we had to start working on the next one. It's like time to upgrade to Rails 4 because Rails 3 was about to be end of life. So by that time, I was a little burned out. I transferred teams to a different team where I could focus more on like product facing work. I'd been a little burned out from the upgrade. And the reason I tell the story, it's not like these upgrades were the only thing the security team asked us to do. They were a new team and they were trying to get the company in good shape. Every week there was a new package that needed to be upgraded. a training we had to take, another form we had to sign, a policy we had to learn. And so we began, unfortunately, to kind of dislike our interactions with the security team. It felt like every time we'd see them, they had an ask. They had more work for us to do. And I think on the engineering team, we didn't really understand what the value of that work was, or at least maybe I was too junior to really thoroughly understand the value of the work. In retrospect, here, I'm sure the work they were doing really was valuable, and as I think back on it, like they were making good choices. But at the time, it just felt like it's kind of getting in our way. And the reason to tell this story is that everything is a trade-off. When you're working with engineering teams, developer time is a little bit of a zero-sum game. And this meant that when we had security asks to handle, it meant we couldn't work on customer-facing work. The customer-facing work didn't go away, so we kind of felt stretched thin on both ends. Trying to do what was right for the business, also meeting the demands of the security team. Eventually, we get features that we needed to build, and I'm sure you felt this with product managers or the engineering team that says, like, hey, we have contractual obligations. We have to build stuff. And then we had reliability issues that we couldn't ignore, and we had to prioritize infrastructure and support. And by that time, we had sort of started to ignore the security team. Their asks were at the end of the to-do list, and we were once again back to real security issues not getting fixed. Truly, this was bad for everybody. This poor relationship was putting the business at risk in a way that I think I didn't really understand at the time. So now pulling ourselves back to the AppSec perspective, who's ever opened up their environment and seen a tab with a big alert that looks like one of these? I'm sure the security team at Meraki was looking at a screen just like this and trying to deal with the situation. They had problems that they knew were a risk to the business, and they needed our time to help fix this. But I think the reality is that if this were really true, that we had 99 plus vulnerabilities that were really dangerous, deployed, exploitable, I think we'd all be fired. We would have all been fired. The business would have been owned. There would have been nothing left. We all know this number isn't really real. So many of those alerts are kind of bogus. They don't represent real risk. But the trick is finding those real dangerous needles in the haystack, because there are threats on this list. There are vulnerabilities on this list that are real risks. So we can't just ignore everything. The real trick is finding those needles without having to overwhelm your team with a huge amount of work. And I think there is like the crux of a lot of the problems with SCA programs. Okay, so in this talk, we're going to talk a little bit about the rise of OSS and what it means for security. Talk about some traditional SCA tools, kind of their architecture, how they work, some of the challenges you run into when rolling out SCA programs and tools, and the way forward, and with reachability analysis, and we just sort of hope this becomes the de facto standard for all SCA tools, that reachability analysis is just like a part of the program. Okay, so let's start with the rise of OSS. It's this trade-off between velocity and risk. So over the last 10 years, this is going to be not news to anyone, open source software usage has increased dramatically. Today, even a small project has thousands of dependencies. In SemGrep Cloud, our cloud app, 99% of the lines of code come from open source dependencies. We're a startup. Our front end is not that complex. Our lock file is 30,000 lines long. We're pulling in a lot of stuff from the ecosystem. On the whole, this is good. These open source projects are solving problems that are generic to all of us. I don't have to spend my time figuring out how to render HTML or parse a cookie. I use React, I use Flask, and I get to move on and use other open source projects that implement this functionality really well. And I get to move on to spend my engineering time on business problems that are unique to my business. The downside that I think many of us and many software engineers don't like fully internalize is that I inherit all of the risks and security issues of these open source projects I depend on. And I think we like make this trade-off without really realizing the implications often. Looking at the rate of vulnerability disclosure for open source projects, it just keeps on going up. Over the last 3 months, we've had more than 8,000 new vulnerabilities disclosed. But it's not like the old vulnerabilities just go away. They're still out there, and hackers keep like blasting the internet, seeing if anyone is using one of the old vulnerable versions. These are logs from a few days ago. We're like catching some spam of attackers trying to like see if we have anything open. We are not a PHP shop. We are not a WordPress shop. So they are just like blasting the internet, seeing if there's anyone out there who's using the vulnerable version. This was, especially funny to us because like it's not anywhere in our technology stack. But we can scope, let's say, those 8,000 of those new disclosures down to the languages and frameworks that you're actually using. You might get, maybe there's tens or hundreds that of a year that of newly disclosed vulnerabilities that are going to impact you. But I think the other multiplier that we don't take into effect is that very few of us are only running one application or one simple application. Many of us are running microservices or multiple services. Many of us have monorepos with multiple lock files in it. And I mean, just like think about how many services your teams are supporting. And then, think about how many alerts you might get in a typical support week. It's not because you're using a bajillion dependencies that all got vulnerabilities at the same time. A single unique disclosure can account for tens or hundreds of vulnerabilities across a large number of projects. So then the security team has to understand the context for each application in order to triage it and determine if it's a real security issue or a false positive or something that can be ignored. So I think the worst part about this, there's a really great talk that Josiah did yesterday on some analysis. He talked about like a study that he did. We did a larger study as well, kind of confirming his analysis. We saw that a huge percentage of vulnerabilities are false positives in a similar way that he showed. We ran a study of, I think, 1,100 popular open source frameworks and showed that about 2% of open source projects showed that about 2% of reported vulnerabilities were theoretically reachable. Never mind exploitable. We're not talking about exploitation, but reachable. We've been able to replicate this study on customer code. It's a little bit higher percentage in enterprise code, but not by much. And this means that SCA programs are typically super low ROI. You spend a ton of time searching for that needle in the haystack, and that haystack is pretty big. Okay. Before we dive into how to fix this, I want to back up a little bit and talk about how we ended up here. Talk about some of the traditional SCA tools that we use. We're here at an OWASP event. Probably a lot of us are using OWASP Dependency Track. I think we have in the audience someone who's working on it here. Some probably use Dependabot. It's just like check a box and it works. Some might use paid solutions like Black Duck and Sneak. Fundamentally, a lot of these tools are kind of similar. There's many differences, but how they find vulnerabilities are often pretty similar. So there's a few pieces. The first is they collect a database of vulnerabilities. You have to start with a knowledge base. They're sourced from public vulnerability databases like NVD. They might have their own security research team that's investigating packages and finding vulnerabilities. Each database entry looks something like this, where there's a package, a vulnerable version, or maybe vulnerable version range, the minimum patched version. Ideally, they'll also be accompanied by information like the severity, a description, a recommendation on how to fix. Often there are references that can help you understand the vulnerability better. The next piece is that they have to have some ability to scan your dependencies, figure out what you're using. Often they might be scanning a manifest file or a lock file, and they might query a build system, but they compile the list, and then the final step is they match the listed versions of your dependencies against the database of known vulnerabilities. They tell you if you have any vulnerable packages. So you end up with a list that looks like this of vulnerable packages in your applications. So what is the issue here? This list is 5 long. But the problem is this is not necessarily a list of vulnerabilities that are exposed in your system. It's a list of packages that have vulnerabilities in your system. The vast majority of packages that might show up in this list may not be dangerous to you based off how they're being used in their applications. For a package to be dangerous, the first-party code must use the vulnerable part of the library, except for some exceptions of packages that are like malicious packages that are vulnerable on install. So this list of 5, you might want to, we'll get to that in a second. So let's take this Lodash vulnerability as an example. So what is Lodash? Lodash is a JavaScript utility library with, as you can see, a few hundred public functions on it. It's really like an amazing library with a ton of utility. It's quite large. How do I get it to go forward? There we go. The vulnerability says that merge with the function is vulnerable to prototype pollution. I think there's been a bunch of talks on what that is. the whole library isn't vulnerable at this version, just this function. And a few more functions are also happen to be vulnerable at this version, but they also have disclosures associated with them, so they will also have database entries associated with them. Some of those like merge and merge deep are also vulnerable to the same vulnerability. But if I say use Loadash's partition method to manipulate an array, I'm safe. Partition is not vulnerable. It doesn't rely on any of the vulnerable methods. There's no undue risk associated with my application. Now, looking back at this list, you might be thinking, like, why not just fix them all? And getting to inbox 0 is great. If there's 5, that might be relatively easy. This is, I think, probably from a side project of mine. It's like, okay, great, I can go fix these. But we all want to live in a world where all vulnerabilities are fixed. But I think many of us work at companies where getting to inbox 0 is just not feasible. And we have to take a more pragmatic approach to solving these problems. So instead, we're closer to here, where we might be having dozens or hundreds, or maybe we just don't know how many vulnerabilities are in our system. So why is it so tough then to get to inbox 0? I think part of this is because I talked at the beginning, upgrades can be expensive. I think like not necessarily as expensive as the upgrade I talked about at the beginning of the talk. We don't expect every package to take a year for us to solve. But even so, organizations are rarely only one version behind. When a vulnerability is disclosed, we might be dozens of versions behind the earliest safe version. In the best case scenario, you have a rock solid test suite. So you can land a patch, make sure that all the tests pass, and then upgrade. But some of those upgrades are going to break functionality, and so you still need the developer bandwidth to fix the upgrades that have breaking changes. Without a really good test suite, I've definitely worked on teams like that. I don't know if you have. You also have to do the manual work to figure out if the changes were breaking in the first place. Then go fix those breaking changes. On top of that, it's not like you're just fixing one vulnerability. You may need to land a fix for each instance of the vulnerability across a breadth of services in your organization. So we're talking about this work really adding up. And we all know security teams have low political capital with developers. We can't risk slowing down the business, asking folks to fix security vulnerabilities that may or may not make a difference. When we send something to the dev team to fix, we really have to be right. Wrong too many times, other teams stop listening. At least that was my experience. I think in order to preserve that political capital, security teams tend to take on a huge toil burden. Triaging each disclosure triaging each disclosure takes time, and for each disclosed vulnerability, that could mean triaging tens or hundreds, even thousands of instances of a vulnerability. Diving into different applications, understanding the context of how everything fits together. And since the disclosures don't end, this is a forever process. A time sync for each disclosure and a continuous eye on how code changes. So our support rotation has this as maybe the number one task that they're required to keep an eye on. But there's a really tough trade-off here. Engineering teams aren't the only ones with competing concerns and not enough time. I think security teams face the exact same pressure, just with a different set of concerns. So security teams are faced with a really tough choice, balancing the value of this program, of a SCA program, and against the resources required to run the program. And because we're in a resource-constrained environment, it's not so easy to make this choice. For some, running a security-focused SCA program just isn't worth it. It's too resource-intensive for too little reward, and so instead the goal becomes meeting the minimum bar for maybe compliance, but maybe turning on it to something that can check a box, maybe ignoring many of the results. But for others, that's just not an option. If you're a visible company, if you have sensitive data, if you're big enough at scale, you just can't accept that risk. The needle in the haystack is too dangerous, and so folks commit to doing that toil, manually triaging the alerts so they can find those few real vulnerabilities. Okay, so this is a terrible choice. I hope I've set up the problem well. To us, I think reachability analysis helps folks move up a level and helps them scale this their SCA program. If leveraged properties, it helps security teams move beyond that choice. So let's talk about sort of the benefits of reachability analysis. I think it's a little bit more than than what meets the eye. There is the typical, like, it does help you prioritize and ignore or deprioritize the less urgent vulnerabilities in favor of the ones that really seem like a threat today. I think one of the other things that it helps is faster. Helps you work faster in the case of incident response. So it helps you find and immediately address the vulnerabilities that are the most pressing today, so we can be strategic with our triage time. And then the other piece is that it really helps us codify acceptable and unacceptable use of certain packages that have known vulnerabilities, so developers can fix their own code and prevent real security issues from being merged in the first place. So what is reachability analysis? How does it work? Reachability analysis is a process by which we check to see if a vulnerability is being used in a vulnerable part of the library is being used. We call it reachable if and when the dangerous part of a vulnerable package is used by the first party code. So let's go over an example here. You might be able to tell this isn't real part of our application. So we import Lodash here, and let's just say it's at the vulnerable version. We see on line 5 evidence of reachability. We see the program has called the dangerous function on the library with untrusted user input coming from line 3. And then on line 8, we can see how a user might be able to get malicious input into the vulnerable function. Here we see a very similar function, same user input, same library, but we're not calling the zip, but we're calling the zip function instead of the merge function. Thus we'd call the vulnerability in this context unreachable because, well, we might import a library that has a vulnerability in it, but we aren't using the vulnerable part of the library. So let's go back to the previous example. And I want to make a really important distinction because I think, like, there's no tool here that's going to be the silver bullet. There's no approach here that's going to automate everything and make your life perfect. A vulnerability might be reachable, but it still might not be exploitable. Exploitability requires a lot more context. You have to understand the environment and the context of the application. You have to understand how it's being used in production. You have to formulate a payload. You have to test it. As such, I think exploitability analysis is it's a really time-consuming process. You want to be careful. It's a valuable thing to do. It's important to do this when you think you might have vulnerability, but it's one that is extremely hard to automate in a robust way. So from this perspective, for this example, we cannot tell if this script is exploitable. We don't have the context that we need to make that distinction. Is it run from the CLI? Is it called by an API and passed unsanitized user input? We don't know. So we can't make any claims. Reachability analysis is a lower bar. Does the code touch the vulnerable part of the library? That's it. And because it's a lower bar, it's typically a lot easier to instrument. So let's talk about what you need to make reachability analysis a reality. So there's 3 components to running reachability analysis in a system. So first, you need an engine of some kind that can detect some pattern. A nice property of reachability analysis is that it can be done with static analysis. You don't need to compile or test it dynamically. You can, if that's your preferred approach, but we can do this statically as well. You just need some tool that can read code and detect dangerous patterns. At R2C, we build and maintain an open source static analysis tool called SemGrep, so we use this. And I'll show some examples of how we use it. On the lightweight side, you can just use grep. It's a search tool. Many of us know how to use it already. Doesn't require you to learn a new API. You might use a language-specific linter, especially if it's already built into your system, like Rubocop or ESLint. You might have access to a closed source tool like CodeQL, and you could maybe wire it up to do something like this as well. I haven't really played with CodeQL much, but I think it has some capability here. The second thing you need is a lock file scanning engine, or a scanning engine. I say lock file because that's what we do with SemGrep, but a bunch of other tools use different means to detect which dependencies you use. There are great tools like this. Dependency Track is one. Dependabot will also tell you this information. The third thing you need is a database of vulnerabilities. So you need to know, you have to have that list. But you also need a list of vulnerable functions for a library or a particular version, and under what conditions they're dangerous. So again, there's no silver bullet here. We're going to talk a little bit about what we do to figure that out. But this is going to require a little bit of work and a decent amount of security knowledge. But essentially, the goal is to flip the script on triaging a vulnerability. Rather than spending your time digging into each of your applications, you spend more time digging into the vulnerability itself. Looking at things like the patch diff, reading the blog post on the disclosure. Maybe Twitter is abuzz with successful exploits. I think Josiah had a great talk on patch extraction yesterday. I recommend if you saw it. I mean, well, you saw it. I hope they release the recording. So he has an interesting approach to this. We've done some similar work to that with R2C at R2C to make understanding the vulnerability even easier. We've also found that there's some great open source databases that have some lists of vulnerable functions. I think OSV has some of these. And then a really cool effort that I want to hype is there's the Global Security Vulnerability Summit are working on trying to provide this information at a disclosure time more readily so that each new disclosure will have more metadata on what it means for this disclosure to be vulnerable. I think this is like a rising tide lifts all ships, so we hope that this becomes an easy part of the exchange. Cool. Let's talk about some examples. I think making this more concrete will be helpful here. So towards the end of 2022, we saw a disclosure in the PyTorch library, some information about it. Looking at the issue in the library itself, I mean, it was nice. It didn't take too long to figure out what was dangerous about it. This is like an example from the issue. Someone had nicely demonstrated the exploits in the issue. So we can see, like, here's the example of the vulnerable function. Here's what an attacker might pass into it in order to successfully exploit. And from here, we can kind of work our way to figuring out how to automate detecting this. So the first part of the engine is the code scanning piece. So we're going to specify, we're going to pick something that works for Python because this is for Python code. So, grep will work across languages. Maybe if Bandit will work if your Python, some grep has Python functionality. It's good to include a message here so that someone who's going to read this finding can understand what to do, and understand the context, because again, they're going to maybe look for exploitability, not just reachability when they're triaging. So providing a high quality message here will help whoever then does triage this vulnerability understand what to look for to see, is this exploitable? Should we really spend the time patching this? And then the pattern is, almost copy and pasted from the disclosure. And this will allow us to check, great, do we actually use the vulnerable function? The second part of the engine, matching against a dependency version. This is semgrep syntax, depends on either, means that you can, maybe there's a range or multiple versions of a package, but pretty simple. You put in which registry it comes from, what the package name is, what the version, the vulnerable version range is. And now we can run the rule against a code base, see if it's used at all, and then also then we can see, okay, is this reachable or unreachable in the context of the places where the vulnerable version exists. Let's look at a slightly more complex example to see how we might construct something if there's a little more complexity. So there's an active record CVE last month, I think, for SQL injection. The disclosure specifically said, this is something that no one should ever pass untrusted input into this. Why would they ever do that? Well, because no one uses code the way you think it's going to be used. So luckily, there are references in this CVE, and I think that, the hope is that more and more CVE disclosures include the reference either to the fix or maybe here we even had a blog post write-up about the disclosure. And so we can look here, thanks to John Hawthorne, whoever you are out there, did a great write-up for this one. But we see the affected versions listed here, so we can make sure that we can be targeted there. And then examples of what the vulnerability might look like in code. So this is where, it looks like there's 3 functions that are vulnerable. We have the annotate function, the optimizer hints function, and then we have the query log tags function. Now, okay, so how do we write our rule? That's a little small, I'm sorry. Again, we want to think about the message. We want to think about what they might be looking for. Here, there's a message here that talks about what exploitation attempts might look like, because it's also important to think about, have we already been owned by this in the case of exploitation? What am I going to go look for in my logs to see if an attacker has gotten access this way? We use the syntax pattern either in semgrep, which allows you to say basically an or, because there's a few different methods. So we have the annotate method, the optimizer hints method, and then the query log tags method. And then because Ruby has a bunch of different ways that you can set variables and call methods, a bunch of other things you have to be able to do for that last one. But none of this is requires super deep code analysis. All of these are doable with grep. You might get a few more false positives. You might be able to instrument a more powerful tool, get a few less false positives, but the approach is basically the same no matter what tool you end up using. Again, we saw multiple version ranges, so it's useful to be able to specify or use a tool that allows you to specify multiple different ranges here, because we saw versions that were vulnerable in 7 and 6.1 and 6.0. This is common on disclosures where you find a disclosure. It's not a disclosure necessarily on the newest code. It might not be a disclosure on the oldest code. It might be something that exists across multiple versions. And they have to, as long as it's not end of lifed, they'll try to patch all of those. Cool. All right. So now we've had an opportunity to look at some rules. Let's talk about how we build this sort of analysis into our SCA program. To do this, I want to zoom out a little bit and think about how vulnerabilities end up in our systems. So there's two main vectors: new disclosures and new commits, or new code. New code isn't quite right. Changed code. The first we're going to talk about is a new disclosure. New disclosures impact old code. Code that hasn't been touched in years. Code that you really thought was safe. Now turns out that your Nokogiri XML parser wasn't safe after all. It's been vulnerable this whole time. We just recently found out about it. And we either need to spend some time sanitizing the input, or we need to upgrade. To do reachability analysis here, you want to be able to run scans at request time here, so ad hoc on a new disclosure. So folks will typically instrument a script that pulls all the important repos and scans the whole repo with a new rule. If you use a solid static analysis tool, these scans are typically dominated by how long it takes to pull the repos rather than the scans itself. So some folks have sort of nightly or hourly cron scans that will sort of take whichever new rules have been created or checked in and scan them on all repos. So you don't have to do the manual work of running the script, waiting for everything to get pulled, waiting for everything to get updated. So instead, when you check it in, it will like auto scan on the next cron run. The second vector is new or changed code. You've scanned and confirmed that at the time of the disclosure, the vulnerability didn't exist in your code base. If only people would just stop changing the code base. But that's not going to happen. I remember so many times we just declared, we should be done. We're done. We're done with this project. Someone might check in a new vulnerability new code that has a vulnerability in it. But I think a common thing that might happen too is you might already be using a package safely, but for the first time you use the reachable function of the vulnerability, moving it from a unreachable vulnerability to reachable. So we need to put a guardrail in place to prevent developers from introducing these new vulnerabilities. To prevent these threats, folks instrument PR scans often to make sure that code changes don't let in any new reachable vulnerabilities. This is ideal because it lets developers self-serve the fix. Maybe you can also instrument PR comments, or maybe you fail the build, and let developers read that message, understand what's happening, and make that fix. You can make it blocking. If you make it blocking, you can really ensure the vulnerability never makes it into production. But you have to be careful there. Blocking scans are a cost. And if you're wrong a lot, you're going to hear about it. Scanning your whole code base for every vulnerability can be time consuming, depending on how many rules you have, depending on how fast your scanning tool is. There are strategies you can do to mitigate this. You might only scan the files changed by the PR. That can really reduce your scan times, limit the number of files that you have to scan. The other thing you can do, if your security posture will allow it, is to run out of band scans, maybe on an hourly basis. So it doesn't block the PR, but allows you to fast follow with the fix that after the vulnerability is introduced. Again, this is going to depend on your risk model, about how much, what your relationship is with your development team. So reachability program, kind of in summary, here's what it looks like in action. You hook up a feed to some vulnerability database so that you get notified when a new vulnerabilities are disclosed. I think many folks probably have something like this strung up with a tool like Dependabot or Dependency Track that lets you know when there's a new vulnerability in place, specifically one that might impact your code base. And then when a vulnerability comes through, rather than jumping into the code to triage, you dig into the vulnerability itself. Is there a single function that's vulnerable? What kind of inputs? Is it only conditionally vulnerable? Try to understand that. Then you write your rule using whatever tool, and you scan your code base, your existing code base finally, you check in the guardrail rule to make sure you don't run into this vulnerability in the future accidentally. Okay, so in summary, reachability lets security teams run a more effective, pragmatic program. By implementing reachability analysis, your AppSec team gets to move a level up from manual toil to automating away current and future work. I want to again say this is not bulletproof. Static analysis is imperfect. There are both false positives and false negatives, as with any analysis technique. But our goal here is not to run a perfect program. Our goal here is to run a pragmatic security program. There are some vulnerabilities that are so bad, you want to excise them no matter what. The Log4j is a good example of this, where I don't know if I would have trusted any tool to tell me I'm safe if I saw it in my system. But I might have used a tool to help me pinpoint where it might be most dangerous. I want to also say it's not a trivial amount of work researching and writing rules for a reachability program, especially for orgs with multiple services and multiple applications, though this lets you scale that research. So instead of doing this research dozens or hundreds of times and then doing it again over time as people introduce new code, this lets you do research one time and then rather than manually triaging each instance, you can triage the few instances that seem to be actually dangerous. If you don't want to run this program yourself, there are products out there that do this. We make one, but there are lots of companies that do this. And I think the hope is that every SCA tool just builds this in. I think like long term, that's the direction that we see the market moving in. And so I hope that all of these tools, open source included, move towards reachability analysis. Security is not a purity test. I think we should believe in pragmatic security, and pragmatic security should not require so much toil. Thank you so much. Great. We're an open source tool. Come join our Slack. Come say hi. We also have a booth out there. We're giving away hats if you want to come talk to us. But I'd love to, talk and hear some questions and talk about it.
Thank you, Mr. Berman. So now we move to the questions.
Thank you very much for the talk. Can you tell me what is the difference with Eclipse Steady? If you ever had heard of it, I mean, it's for Java, but yeah.
Yeah, I think there are, Josiah talked about this too. There's some tools out there that are language specific. I think Go Vulncheck has one too for Go. These databases are great. The tools are excellent. I don't know that much about Eclipse Steady in particular. I think one of the differences is automated patch extraction is like a choice that your team is going to have to make. If it's fully automated, you're going to end up, as Josiah talked about, with a much lower recall rate. Building a human into that loop can help you increase your recall rate. But again, that's a scalability question, right? So we're talking about pragmatic security, and if your team doesn't have the resources for it, using something like Eclipse Steady, even though you might miss a few things, will still be really like an excellent step forward for sure.
Something they do also that might be interesting for you, they use dynamic analysis as well. So what they do as well is kind of instrumentation. So they use the unit tests that are available to see whether after the reachability analysis, there is also some test going on the vulnerable path, on the potentially vulnerable path.
Right.
So are you considering adding that in your case as well?
I think we're considering, I think, like a lot of things. I think what we hear is the trade-off between static and dynamic analysis is that static analysis is going to miss some of those things. Dynamic analysis is going to miss the things that you don't write the tests for. And so I think at the end of the day, you need both, and you need a good test suite. You also get the advantage of the better your test suite, the easier those upgrades become because you're worried less and less about the breaking changes.
So I agree that there might be a lot of noise if you don't do the reachable analysis, but don't you agree that it's a good idea to keep your dependencies up to date anyways, like you saw in your first company that maybe you didn't have a reachable vulnerability for 11 years, but maybe you should have updated Ruby on Rails anyways?
Yeah, I think that's a great point. I think that the hard part is that we're prioritizing. It's not as simple as saying, well, we should just all upgrade all of them all the time. I think we're like prioritizing it against other business needs. I think it's a hard counterfactual to prove, but like maybe the company never succeeds. Maybe the company doesn't get acquired and have like a positive outcome, doesn't get any penetration if they're spending too much time on security things. We would look at the code base and we'd see things like a comment that said like, we should get around to fixing this. And it was written in 2007. And we're like, some people would say, that's terrible. How do we let this sit for so long? And on the other hand, you can think of it as we got away with not doing this work for a really long time. And we got to prioritize other more important things. So I think it's a trade-off. I think a good practice now, because there are much better tools, is if you can get to the point of automatic upgrades, that's excellent. I think automatic upgrades, though, may require you to have an excellent test suite, which again is going to require a lot of investment. So again, it's like, this is the least satisfying answer ever. It depends.
Do you have any stats on, out of the CWEs and Cs, whatever, how many actually tell you which method is the one? Because I tend to think that's very little. Yeah,
if I'm remembering right, there's a couple hundred in the GitHub advisory database, maybe 120, 150, something like that. We were like just pouring through these results earlier. Go Volncheck has like, I think, a complete list of all of them. But I think, so I think like there's going to need to be a combination of approaches here. Some of them are going to be provided for you. Some you can do sort of like patch, what did they call it? Like patch lifting from the fixes. I think most CVEs now have references to the commit with the fix, which then allows you to eventually like wire up automation to at least pull some stuff out of it.
We have a question here.
So 2 questions. One, for the reachability, you were scanning the merge function that was vulnerable. Are you also scanning the actual third-party dependency to see if the zip function calls the merge function?
So this is where there's like a human in the loop. So I think the base of the question is, are you looking for if child functions, if like helper function, a vulnerable helper function might be being called by multiple functions. So
somewhere in the call stack.
Right, somewhere in the call stack. So I think we're not like walking the whole flow graph. Right now we're doing that, like in our team, we're doing this manually, where we go and we look through the code, look through the patch diff, and then we actually use semgrep to see, okay, where is this function called? And then we use semgrep to say, where is that function called? And so we can like walk that with semgrep to figure out the list of public functions that are exposed by the vulnerability. We happen to know with this example that like partition doesn't call merge, and so we know that partition is safe. We also find that for a lot of functions, for a lot of disclosures, like researchers are incentivized to get all of the disclosures out. So there will be a large list of all of the possible public functions, either a part of the same CVE or as multiple CVEs.
An awful lot of the work that you're putting in is very, very valuable. You're actually validating the functions there. You're pulling it out of the description and stuff like that. Things like the OSV dev standard, that structure has the capability to have the function names in there. Are you looking at resubmitting those back in so the actual vulnerability is updated with the functions in the appropriate place? Yeah,
I think we're exploring partnering with them to make sure that we can provide that data. There's a question of like there's a question of like commercial stuff there as well.
So I have a follow-up question on that. So do you currently have a proprietary data with all these vulnerable functions with the vulnerability, or do you just currently aggregate all the public open one, or how you're handling that, and are you publishing any of your reachability data for open source project anywhere, like the ones you did internally for open source project?
Yeah, good question. So we do have our own database. I think we consider it like we're enriching existing databases with the lists of functions and keeping that as our database, and then we're looking to explore like the commercial viability of opening that up. I think there's a question of like, how do we do it in such a way that like respects our business and also is useful for like practitioners.
Hey, a super good presentation. I like the methodology you're using. I think I'm thinking more on the maturity side because one of the things you have is like 100 to 1 if engineers or developers to security people, and 10 to 1 in DevOps or to security people. So like all of this work can be done by any of those teams.
Sure.
But we are putting some more strain on the security team.
Sure.
So it's like the less people you have, and we are actually getting them more work.
Yeah.
Right? So I think it depends a lot on how mature is your organization and how you can do, because if you're a very small startup and you prioritize other things, then probably your cloud posture is really bad and other things are really bad.
Yeah.
So the security team has a lot of stress and doing other things right also. I think there is a trade-off here that it's really interesting.
For sure. And I think an interesting part here is exactly what you said. This doesn't necessarily require an AppSec person to be the person who does writes the reachability rule. In fact, you might want instead like an expert in the ecosystem to be the one writing the rule, because they'll be able to understand the more tricky trade-offs there. I think Tanya earlier talked about like a security champions program. I think we see a lot of people transitioning their SCA program so that teams are responsible for patching so the developer teams are responsible for patching the services that they own. I imagine this is going to, like, you can run a similar sort of program where they're responsible for patching. They may also be responsible for writing a reachability rule to prove that they don't need to patch. And you can kind of run a program that way as well.
Is there any other question?
A couple people up front.
So, original SaaS is very, very slow.
Mhm.
And then next gen SaaS is faster.
Yeah.
Dast is really slow.
Mhm.
And so it's easy for me to say to a dev, hey, like SCA will take like a millisecond and your thing is it just checks what you've got and cross-reference. So if we're going to do reachability, how much latency are we expecting? Like seconds, minutes, hours?
Yeah, hopefully not hours. I think the philosophy we have is that it can't be any slower than your tests. Security never wants to be the reason that that the developer is waiting on a PR. So if your tests are fast, let's make sure your reachability tool is fast. If your tests are slow, well, let's make sure your reachability tool is fast and let's speed up the tests, I guess. But so you can start with like a super lightweight tool, like, ripgrep is something that's pretty lightweight, very fast. That's going to do reachability. That's going to give you some like lightweight reachability analysis. We find that semgrep is extremely fast, runs in the order of seconds. But it's going to depend. If you're trying to scan your whole repo with thousands of rules, every single merge, that may not be the best approach. So again, you're trying to figure out that pragmatic approach where you're saying, okay, what am I looking for here? Can I just scan the code that was touched by this PR? Can I just scan it with rules that are about this language? Can I figure out ways to reduce what I need to scan and then to use tools that are fast? I think exactly a good point. Yeah.
Just to slightly expand.
Yeah.
Let's say you take the normal to, just for say, let's say we see case of that.
Yeah.
And we scan something with any reachability.
Yeah.
And return reachability and we scan it again.
Yeah.
Can we expect like seconds, minutes, hours in between how long one is versus the other for the same app? Like let's say 20,000 lines of code. I realize that everything on the spot.
Yeah.
Like when I found out that our original SaaS could take 18 hours, I was like, oh my god! So it's
Yeah.
important that I brace developers for what comes.
Yeah, I think we're looking at like high numbers of seconds typically. I think, maybe 1 or 2 minutes in a bad case is typically what we're looking at. Yeah, and that's like maybe scanning a whole code base with some number of rules. There's like, again, so you're going to it's like going to be like multiplying lines of code by number of rules. And then anything you can do to take that down. There's also some amount of like rule complexity can make your scans more time intensive. So if you're trying to do with your scans multi-file analysis where you're doing source to sync, that might reduce false positives. It might really blow up scan times. So you might think of like that as a tool you might use in another environment. So yeah, thank you. Great question. Thank you.
Did you use any other data sources outside of things like CVSS or any other scoring systems to help kind of prioritize what reachability rules you went after?
Yeah, I think so. One of the things we looked at, so I don't know if this is aside from CVSS, we like look for vulnerabilities that are impacting lots of people, and then also ones that have active exploits. So one of the things we'll do is, I don't know if folks always want to wait around for the disclosure before they start investigating. Log4j, I think like the whole world knew about it before the disclosure came out because Twitter was abuzz. And in that case, it seems like there's an active exploit. In fact, you can like copy and paste some lines of code and start scanning the internet and see what the active exploit is. At that point, you might want to be prioritizing that over the disclosed ones that say high severity or critical. So there's databases of this too that have like, VulnDB and other tools will tell you some things about whether or not there are active exploits in the wild. And then the other part that we see is, so when we're like looking to see which rules to write for us, if, let's say 50 disclosure were to all come out in the same day, we might run before we do the reachability analysis, we might run a scan of just, does the package exist with the vulnerable version across all of our repos, see how many repos fire for which CVE, and then prioritize the reachability ones that have a high count. So if, we have let's say we have one Python repo and 10 JavaScript repos, and each of the JavaScript ones has the vulnerable version, we might prioritize that JavaScript, writing the reachability for the JavaScript vulnerability first.
When working with developers, did you notice that they were like more willing to accept the reachability analysis results and work on those, or they were still pushing back, asking, demonstrate me that it's exploitable? Yeah,
I think that the interesting part is, I think for reachability analysis, the proof positive is really powerful. You can point exactly to the line of code and like you say to the developer, look at this line, then you make a call. And I think it's important then, the big distinction is to write a really high quality message. If you can explain what they should be looking for, under what circumstances it might be exploitable, they're technical, they'll read the code, they'll read the message, and then they'll be able to make a judgment call as well. And so you're putting some trust in them, but they're putting some trust in you as well, that the tool is going to be high quality. I think the harder thing is getting folks to agree on the non-reachable pieces. And so there's some tactics there too. So developers probably aren't going to care. Developers don't want to be paying attention to those anyway. But your teammates, yourself, might not be feeling that confident when you say, hey, I want to ignore this. So some things you can do there, you can use the same reachability tool you're writing, but write a more permissive rule, a more sensitive rule. See okay, is this package being used at all? What functions are being called at all? See those results and then gain some confidence yourself that, great, this really does look not reachable.
So any other question?
Okay, thanks for the talk. Just on that point about reachable versus non-reachable exploits, say we find one and it's not reachable. Yeah. Is that then justification to scan every commit in case it becomes reachable? Or do we just do developer education and say, hey, would you mind, not doing this until we get to that low priority issue of a non-reachable issue?
I think it's useful to lock in the guardrail because you're going to say we just know the code is going to change over time. I think Lodash is a good example of this, where it's a utility library. There are a ton of functions on it. And just because someone isn't using merge with today doesn't mean they won't use it tomorrow, because it might have valuable functionality. And it's not necessarily a blocker to a developer to say, hey, don't use this. There are other libraries that give you merge functionality. There are other ways that you can solve this problem. And maybe they'll be motivated and they'll go fix upgrade the library as well. But I think, so it's going to depend a little bit on your risk profile. Maybe you're really strapped and you don't have the time to start building it into PR scans. That's fine too. It's better. You've at least had a validation that it doesn't exist in your code today, but it's really useful to lock in that guardrail to make sure it doesn't exist in your code tomorrow as well.
Any questions? Apparently not. Great. Thank you, Mr. Berman.
Yeah, thank you so much.